to all of you. Today we are going to study instruction set of 8086 microprocessor. This topic is under Unit 3 of subject KCS 403, which is a core subject of Computer Science branch of second year students. So, what is an instruction set? In 8086 microprocessor, an instruction consists of 16-bit data, and these data will be fetched from memory with 20-bit address lines. So, 8086 can perform any mathematical operation on byte/word operands. Now, to perform any operation, it requires an instruction which consists of two parts, that is opcode and operands. So, the way opcode will inform that what operation needs to perform by microprocessor, whereas operand will give the data on which instruction performs that specified operation. So, if we talk about instruction cycle, it consists of two cycles, that is to fetch opcode from memory, that is called as fetch cycle, and to fetch data from memory, it is called as execute cycle. And the way in which microprocessor completes an instruction consists of fetch cycle and execute cycle. So, the complete list of instructions performed by a microprocessor is called as instruction set. So, 8086 supports 6 different types of instruction sets, which are classified as data transfer. In data transfer instruction, the data, that is 8/16-bit data, is just copied from source to destination. That's why it is called as data transfer, because only byte/word operand is copied from source to destination. Whereas in case of arithmetic instructions, it performs all the mathematical operations, that is add, subtract, increment, decrement, multiply, divide. Now, moving towards logical instructions. In logical instructions, it consists of AND, OR, XOR, NOT, compare, then shift and rotate instructions. Next, moving towards string manipulation instructions. String are a class of data in 8086 where a set of data is taken from one place to another. So, string means a set of byte or word. So, there are certain instructions like move, load, store works on string group. Then there are processor control group, which instructs the machine, that is halt, no operation, and so on. And last is control transfer group, which change the sequence of execution of 8086 microprocessor. So, we will start with the very first group, that is data transfer group. So, in data transfer group, the instructions are used to transfer data or address into registers, memory location or IO. So, basically there are two operands, one is called as source and other is called as destination, and it just copies the data from source to destination. And both the operands must be of same size, that is either both will be word or both will be byte. For example, if we write move AX, BX, both are 16-bit registers and it copies the 16-bit data from BX register to AX register. Similarly, we talk about byte operation, that is move AL, BL, then it copies 8-bit data from BL register to AL register. Whereas if we write move AX comma BL, it is 8-bit and it is 16-bit, so this operation cannot be possible, it gives error. So both the operands must be of same size. Now, what is source and what is destination? A source operand can be register, a memory location or an immediate data. Whereas destination can never be immediate operand. So destination can be register or memory location only. And size is of byte or word. So move operation simply copies 8-bit oblique 16-bit data from source to destination. We will check this taking some examples. So the first very important instruction using move in data transfer group is move. In move instruction, there are one source and one is the destination operand. So destination can never be immediate operand. So it can be register oblique memory. Whereas source can be register oblique memory oblique 8 or 16-bit data. So move operation is used to copy data from source to destination. As we can say from this example, the value of register 1 is copied to register 2, or we can write it as register 1 to memory location 2, or we can write as memory to register. But both the operands can never be registered at the same time. So if we talk about one example, the example of first type of instruction is move AX, BX, both are registers. The example of second instruction is move BX, which points to the memory location, AX. So it copies the value of AX to memory location with the physical address BS into 10 plus BX. It will calculate the 20-bit physical address, and the AX value of AX will be copied to address and address plus 1 locations respectively. Similarly, in second operation, we can write it as move AX, BX. So value of memory location is copied to register. If we talk about immediate data can only be source operand, can never be destination operand. So it just copies data to register or memory location. For example, if we give 8-bit data, it is AL, 32. For 16-bit data, we can write move AX, 32, 52. And if we write any memory location, then move BX, 2000. So this copies the 2000 value to address given by DS into 10 plus BX. It gives the physical address, and address plus 1 location are the two locations wherein this value will be copied. So in this way move operation will work. Move operation simply copies source to destination, whereas interchange the content of two locations. That is, in exchange, the value of register or memory are interchanged. Like if both the operands, that is register 2 oblique register 1, then the content of register 1 will be copied to 2 and vice versa. Whereas if destination is memory and the source is register, then it simply copies the content of register to memory location and memory location to register. For example, if we write exchange AL, BL, then value of AL will be copied to BL and BL will be copied to AL. Whereas if we write move, then only BL value will be copied to AL, but reverse will not be true. So exchange instruction is used to interchange the content of register to register or memory location. Now push. The previous two instructions work on normal memory, whereas push and pop works on stack memory. Stack memory is a special type of memory which is LIFO, that is last in first out. So stack pointer always points to the top filled location of stack. And if we have to write onto a stack, then we have to move to blank location, that is SP minus 1. Write 1 byte in this location and then again move to another location and write another byte into next location. So push register is used to write 16-bit value onto stack memory. So the physical address will be calculated by stack segment into 10 plus stack pointer. It will give the physical address. The content of register will be copied to 2 locations at this physical address. That is, first of all lower byte, then higher byte. So if we say that stack segment is 2000 and stack pointer is 3000, then the physical address will be 23,000. So 23,000 points to memory address. It reduces it by 1, that is 2, 2, F, 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 that is this address minus 1, and copies lower byte of 16-bit register to this location. Again it do it minus 1, 2, 2, F, F, E, and copies higher byte into this location. So this instruction copies higher byte and lower byte into memory address minus 1 and minus 2 location, and the current stack pointer will become SP minus 2. Similarly, the source of instead of register, we can take the value from memory location also. So it copies the value from memory location to stack segment with SP minus 1 and SP minus 2 effective address. The reverse of push is pop operation, that is, to read out data from stack memory we use pop operations, and the address is calculated in very similar manner, that is SS into 10 plus SP, and the content of address and address plus 1 gives higher byte and lower byte. Since top of stack will become next SP, so the content of SP is copied to higher byte and the content of SP plus 1 is copied to lower byte of register or memory location. And then at last the stack pointer will become SP plus 2. So pop is just the reverse operation of push. Push is used to write onto stack memory, whereas pop is used to read out 16-bit data from stack memory. Next is in and out instructions. In and out instructions are used to read or write data into IO port. In and out are of 2 types, that is direct and indirect memory addressing. In case of indirect memory addressing, the port address is specified in DX register. This is indirect addressing. The port address is given in DX register and 2 to the power 16 IO ports can be accessed using DX register. So the in AL comma DX means the address of memory is DX and the value of this port is copied to AL. Similarly, if we write in AX comma DX, then the address is given in DX and address plus 1 values are copied to AX. If we talk about direct IO addressing, then the 8-bit address is directly specified in the instruction. So in case of direct, only 2 to the power 8 IOs can be accessed, whereas in case of indirect, 2 to the power 16 IOs can be accessed through instruction. So in case of direct addressing, in A comma address means this is the 8-bit address which is directly specified in the instruction and the value of this address is copied to AL or AX registers. Out instruction is just the reverse of in, that is the value of accumulator is copied to the port address either specified by DX register in indirect mode or the address is directly given in instruction in direct mode. So in and out are the two instructions which are used with IO port. In is used to take data from IO port. Out is used to copy data into IO port. These both instructions work either in direct or indirect addressing mode. In case of direct addressing, address 8-bit address is directly specified in the instruction and 2 to the power 8 IOs can be accessed in direct addressing mode. Whereas in case of indirect addressing, the 16-bit port address is specified in DX register, that is 2 to the power 16 IOs can be accessed in direct mode, and this address through DX register will give the data to accumulator in and will copy the data from accumulator in out instruction. Now we move towards arithmetic group. In case of arithmetic group, as I have already told you, it consists of plus, minus, increment, decrement, multiply, divide and so on. So in case of add instruction, two operands are specified. So one operand will be in register source destination and other is source. If we write it in generalized form, add destination comma source, then this instruction simply add both the values and copied it to destination, that is first operand. So if we write add register oblique memory comma register oblique memory, that simply this instruction simply add these two values and copies it into register 2, or add register with memory location or memory with register location and copies it to the destination operand. So add destination comma register, both operand destination can be register or memory location or immediate but can never be immediate data, whereas source can be register or memory location or can be 8/16-bit immediate data. So if we write about immediate data, then it consists of register or memory plus immediate data and copies it into register or memory location. For example, add AX comma BX. So it copies the value of AX and BX and save it into AX register. If we write add AX comma square bracket में BX, then BX points to the memory with effective address BX and the total physical address will be DS into 10 plus BX. It moves to this address, take out the data from this address and address plus 1 location, add it with AX register and copies to AX register. Similarly, vice versa also works, that is BX comma AX. So it add value of AX with memory content with effective address BX and BX plus 1 and save the result at memory location. Also there can be instruction with data and both the operands must be of same size. So add AL comma 8-bit data or add AX comma 16-bit data. So two important things are there, as similar to move instruction, that both the operands must be of same size. Destination can never be immediate data. This is the similar instruction as the case of add, but it is simply add destination plus source plus carry flag and copies it to destination location. So add with carry, simply write destination comma source. So it add destination, source and carry flag and copies it to destination location. Again the same logic works here, that both the operands should be of same size. Destination can be register or memory location only, whereas source can be register or memory location or immediate data of 8 or 16 bit. So the same example work here, that is register plus carry flag or register plus memory plus carry flag, register plus data plus carry flag, or memory plus data plus carry flag. So same operation works here also. Next is subtract. Similar to addition, here there's the operation changes. In case of subtract, it simply subtract destination minus source and copies it to destination location. Again same rule follows, that is both the operands must be of same size. Destination can be register or memory location, whereas source can be register or memory location or 8/16-bit data. Next is similar to ADC, it is subtract with borrow. So if we write SBB destination comma source, then it gives destination minus source minus carry flag and copies it to destination. All other rules will be same, that is both must be of same size and both the operands can never be memory location, both the operands can never be immediate data, destination can never be immediate data, and source can be register or memory or immediate data. Next is increment. Increment simply adds 1. So here only one operand will be there. Increment destination, then it add plus 1 and copies it to same location. So the operand can be register or memory location, but it can never be immediate data because immediate data can never be destination. So in case of increment and decrement, it gives plus 1 or minus 1, and operands can be either in register or memory location. For example, INCAX. It adds 1 to AX and copies it to same location. DEC square bracket BX. So BX is the effective address of memory location. The physical address can be calculated by DS into 10 plus BX, and it adds 1 to this location. So in this instruction, operand can never be immediate data. Next is multiply. 8086 microprocessor, unlike 85, support multiply and divide instructions also. So in case of multiply operation can be of byte or word operation. And here one operand will be by default AX, that is accumulator, and the other operand will be specified either in register or memory location. So it's simply in case of byte operation, the result will be 16-bit and both the operands will be of 8-bit. So one operand will be by default in AL register and other operand will be provided by register. It will multiply both the operand and the result will be copied to AX register. For word operation, it multiply AX with one operand will be by default in AX register and gives the value of second operand in register. Multiply both the values and copies higher 16-bit into DX and lower 16-bit into AX register. So for byte operation, AL multiplied by register oblique memory location of 8-bit will be given to AX, whereas for word operation, AX multiplied by register oblique memory of 16-bit and copies it to DX colon AX, which is of 32-bit. Multiply and I multiply works in exactly same manner, but multiply instruction is basically unsigned multiplication, whereas I multiply is signed multiplication. All remaining things will be same, that is, for signed numbers we write I multiply, whereas for unsigned numbers we write multiply simply. Next is divide instruction. Divide instruction also works on byte oblique word. And for divide, there are two outputs. One is quotient and another is remainder. So for byte means 16-bit by 8-bit division. Why it is called as byte operation? Because both the quotient and remainder will be of 8-bit. So 16-bit in case of byte operation, that is 16-bit by 8-bit, one, that is dividend, will always be in AX register, and second operand, that is divisor, will be provided by register or memory location of 8-bit. This division will generate two outputs, one is quotient and another is remainder. Quotient will be in AL register. After this operation, AL will consist of quotient and AH will consist of remainder. Both are of 8-bit. In case of word operation, dividend will be in DX, AX and divisor of 32-bit, and 16-bit divisor is provided in register oblique memory operand of 16-bit. Again, this operation consists of two results. One is quotient and another is remainder. Quotient will be contained in AX register and remainder will be there in DX register. So divide can be of byte or word, means the quotient and remainder can be of byte type or word type. It depends on type of operation. In case of byte, it is 16-bit by 8-bit division. Dividend will be in AX and second operand, that is divisor, will be provided in the instruction either in register or memory location. Similarly, for word, that is 32-bit by 8-bit, dividend will be in DX, AX by default, and the second bit divisor will be provided by register oblique memory location. And the result will be contained in AL or AH in case of byte operation. AL consists of quotient and AH consists of remainder. Whereas for word operation, AX and DX will contain quotient and remainder respectively. I divide work in exactly same manner. Again, division means unsigned division, that is, it works for unsigned numbers, whereas I division means signed division. Simply this difference, else everything will remain the same. So division means unsigned number division, whereas if there is an I symbol, that means it's work for signed numbers only. Next is compare instruction. Compare instruction works in exactly same manner, that is, the first operand minus second operand, it performs the subtraction. Compare instruction is similar to subtraction operation, that is, first operand minus second operand, and based on this subtraction, the result will not be changed, only the value of flags will be modified. So both the operands can be register or memory location, but both the operands can never be memory at the same time. So it compares, that is, perform first operand minus second operand, and based on that it update the flags. So if register 2 is registered then greater than register 1, then carry flag will be 0 because no borrow will be there. Result is positive, so sign flag will be 0, and result is non-zero, so 0 flag will be 0. When first operand is less than second operand, carry flag is 1, 0 flag is 0, and negative result, so sign flag is 1. And when both the operands are equal, carry 0, 0 flag 1, and sign flag 0. So in this way, these three flags will show the result, whereas all the flags will be updated by this operation. So I hope the arithmetic instruction group is clear to all of you. So in this video, I have covered data transfer and arithmetic group instruction group of 8086 microprocessor. In next videos, we will cover the remaining 4 type of instruction sets of 86 microprocessor. Thank you.